From the free body diagram of this vibrating block, the differential equation of motion, or the general equation of motion, is as shown here, which is the mass times the acceleration plus the damping times the velocity plus stiffness times displacement is equals uh, to a force with respect to time. So what is vibration? It is a mechanical phenomenon whereby oscillation occur about an equilibrium point, and it is classified into two types, which is the free vibration and forced vibration. Free vibration is a system put out of its equilibrium position and vibrates under the action of forces inherent in the system, and in the absence of external forces is under free vibration. So meaning to say, if you have this vibrating block, you set it on an initial displacement and then you uh, let it go, and then it continues to vibrate until it stops. So that is the free vibration. And then forced vibration, a vibration that takes place under the action of external forces. Also, vibration is classified into two, which is the damp and undamp vibration. In damp vibration, where your C, or the damping, is not equal to zero, it allows your structure to vibrate, and then eventually it will stop. But on undamp vibration, it will allow your structure to vibrate uh, for a long period of time. So for the workflow of dynamic analysis for pedestrian bridges, first of all, we need to assess the traffic and determine the limit frequency. And then next, we must perform the free vibration analysis to obtain the natural frequency of the structure. Next, we must determine the pedestrian time forcing function, and then apply the time forcing function along the length of the bridge, maintaining constant pedestrian velocity. And then last, check for the acceleration time response and determine peak acceleration. So to determine the limit frequency, here are some compilation of the frequency range values given in various articles and regulations, has given rise to the following table. So from Eurocode 2, um, it is limited to 1.6 Hz and 2.4 Hz, were specified between 2.5 and 5 Hz, uh, and so on. But um, in our discussion for today, we will be using a limit of 5 Hz. So let us go now to the modeling of the bridge. So I have here the new project Midas Gen file, where you can see I've already added the material properties for steel, concrete, and the section properties. So there are two ways on how you can add your properties, or I mean three ways. The first way is to add it manually. So if you go to properties and then click material properties, then you can add your material properties. The other way is by using import. So if you use import, you can import material properties or section properties from other files. For example, For example, if I will delete these two, and then if I click import, then from a different file, as you can see, this is the materials from the other file. If I click OK, then it will automatically add to the new project. Same with the section. And then the other way is by using the MGT command shell. So I will discuss MGT command shell later once we model now our structure. So this will be our model. It is a truss bridge with an elevation of with this elevation 48 meters span, 5 meters height from top chord to the bottom chord, and then a width of 6 meter. So to model that, uh, there are also three ways on how we can model that. The first way is by using the manual modeling, which you can create your node, translate your node, create your elements, connect the nodes, etc. The other one is using the truss wizard to create the uh, truss bridge. So in this truss wizard, you can just select the type, uh, the the type of the webs. What do you want to what do you want to be the figure of your webs, and then the number of panels. So let's try. So as you can see, the drawings below will also change. So meaning this will be your guide once you are setting up your values here. You can also select if it will be symmetric or asymmetric. So but for today's presentation, we will be using the MGT command shell. So if you go to tools, click MGT command shell, and then you may click open this one, or you may type here the commands. So let me just so for the geometry, I have prepared a uh, text document. Let's open this, where you can see the nodes, which is patterned to MGT command shell nodes, and then the elements. So by doing that, I will not do the manual modeling. So by using the MGT command shell, I can now import the nodes and the elements directly to the model. But if you want to model it manually, since you have attended our previous webinar, I believe that you can do it by just knowing what are the parts of the what are the components of the elements on your bridge. Like for example, what is this section, what is the length, and etc. So if I click this text document, click open, and then it will automatically copy all the files on the text document. And then if I click run, and then you will have your model now. So I'll just change the color. So once you have your model, the next thing we can do is we will add the boundary conditions. So to add the boundary condition, let's go to boundary and then click define supports. But first, let us check the properties. Let's check the vertical elements. So there you have it, your vertical sections, diagonals, top horizontal, top chord, bottom chord, bracing, cross girder, stringer beams, and then your slab. So take note that in this model, I set my diagonal and the bracing into truss element. So these are the input parameters or properties of the sections for vertical, diagonal, top horizontal, top chord, bottom chord, bracing, cross girder, stringer beam, and then your slab. So next, let's add the boundary condition. So the boundary condition that I assume here is that it is a simply supported uh, bridge or pedestrian bridge. So I assume that in this part it is a hinge, and then this one is a roller acting. If you create a section of this part, you will see that it is a simply supported, and then if you create a section of this part up to this part, as you can see, it is also a simply supported, and then and so on. So for the boundary condition in this part, I will use only dx, dy, dz, and then on this part, I will use dx and dz. For this part, I will use dy and dz, and then for the last part, I will be using only dz. So let's apply the supports. So d all for this part, and then click apply. For this part, I will be using dz only, dz and dx. And then this part, I will be using dz and dy. So the boundary condition depends on uh, how your truss will act on your uh, or how your bridge will act on your substructure. So in this model, I assume that it is simply supported to the substructure. So this part dz. So I have now my boundary condition. Then next, let's add the static load case. So go to loads. So let us see. For the static load cases, I only add the self weight, the concrete barrier, and then the superimposed dead load. The live load that that we will be using is subjected to time history function. So let us add these three loads, static loads, SWCP and SIDL. So go to loads, click static load case, first one, self weight, click add. Next one, CB or concrete barrier, then add plus SIDL or superimposed dead load, and then click add. Next, let's add the loads. So let's check. So for the self weight, um, I add the self weight factor at C equals 1, and then uh, this negative 12.5 kilonewton per meter beam load is the weight of the slab. So let me explain this part. So what I did here, if I select these properties, this concrete property of slab, you will see that I've assumed zero weight density, so that it will just become a an element that will transfer the forces to the stringer and the uh, the bottom chords. So what I did is uh, the self weight of that slab, I converted it into uniform loads acting on the stringer, and then it will be passed on the uh, bottom chord of the truss. So let's now add the loads. First one, self weight negative 12.5, then for the CB negative 10 and SIDL negative 5. So we'll add element load, and then let me select the. So as you can see also, I've noted here for the negative 12.5 it is applied on the stringer, and then for the negative 10 it is applied on the bottom chord, and then for the negative 5 it is applied on the stringer also. So if I click, let's select all the stringer beam first, and then let's add the self weight, which is negative 12.5. Click add or apply, I mean. And then for the CB, negative 10, which is applied on bottom chord. Last, SIDL, negative 5, stringer. So we have now our element loads. Let's add the self weight. Self weight load case name will be self weight or SW. Then Z equals negative 1. Click add. And then next, let us add let's convert the self weight into masses, so that this one will be used for the free vibration analysis. So convert self weight into masses and then convert it to x, y, and z direction. Since it is only the elements that was um, converted into masses, all other dead loads must be converted as well. So to do that, we go to loads and then click loads to masses. Mass direction will be XYZ, and then let's add the SW, which where we put the negative 12.5 uniform load, CB, and then the SIDL, and then click OK. So to check that, you can see here in the tree menu if you already added the loads to masses. So as you can see, it is 3 here, which means you add all the 3 load cases in to load to masses. Next, we can now perform the analysis. So before we perform the analysis, let us go first to eigenvalue, and then let's use eigenvectors. Yes, eigenvector then land cost. Then the number frequency, let's set it to 15. So what we will be doing first is we will do a free vibration analysis. So by doing this, we can get the natural frequency of the structure. So let's click OK, and then let us perform the analysis. So let me just check the reaction first. Okay. So next, to determine the frequency or the natural frequency, let's go to result tables and then click vibration mode shapes. Click OK. So as you can see here, um, you have your eigenvalue analysis table and your modal participation masses printout. So as you can see in this modal participation masses printout, on mode 1, the dominant mass is at translational Z, meaning vertical. So this mode 1 is uh, for the vertical displacement. And then for the translational, so it is the mode 2. So this is the mode with the dominant mass. And then for the rotation, it is the mode 3. So let's check. So if I go to mode shapes and then click vibration mode shapes, so mode 1, and then let's uh, display the XYZ direction, click apply. So as you can see, so it deflects vertically. For mode 2, laterally, and then for mode 3, so torsionally. So let's go back to the table. So for that modes 1, 2, and 3, which is this one, if we look at this eigenvalue analysis table, from this first three, which is the mode 1, mode 2, and mode 3, we can get the frequency for the horizontal and for the vertical and lateral motion. For the vertical, we have 2.1695 hertz, which is less than 5. So we need to check for the vertical. But for the lateral, it is 2.5786 and 3.5439, which is greater than 2.5. So no need to check. So we only need to check the vertical uh, uh, motion of the bridge. So this is the- so from the results, the vertical vibration has a natural frequency of 2.1695 hertz. So we need to check. And then for the uh, lateral vibration, it is 2.5786. So it is not required. So the basis of my frequency limit is in accordance to Eurocode. So if there are other codes, uh, that you want to apply, then you can just check it if it is satisfying or not. So we use the free vibration analysis to generate the fundamental natural frequency of the structures, which is from the eigenvalue analysis, we get the 2.1695. So next, we will be doing the time history analysis. So to do the time history analysis, first we must add the time history function. The time history load case. Then we will add the time history function, and then we will add the forces. So to do that, in MIDASGen, if you go to load and then dynamic loads, and then click the load case under time history analysis data. So in this part, click load cases, click add. So we will add three load cases, namely uh, walking, jogging, and then crowded condition. We will be using damping ratio of 3% for steel, and then let's use an end time of 40 seconds for all condition or for all cases. So almost the same input, but the difference on the crowded condition, we will be using a periodic type uh, time history. So let's add the first load case, which is walking. End time 40 seconds, and then uh, damping ratio 0.03. So let's say use an increment output of 1, and then time increment of 0.01. Click apply. Next, jogging. Same input, and then click apply. Last one is the crowded. So let's just say crowd, and yeah, crowded condition, and then periodic, and then click OK. So we have now our load cases. Next, let's add the time history functions. So to add the time history functions, so to add this function uh, on our model, I've created here an Excel file where I can generate um, the forcing function as per Eurocode 1991-2. So this is the reference code to get the force, and then for the input parameters, I have a span of 48 meters. Number division, this is for the stringers, which is 3. What we will do is we will apply the, so let's So what we will do is we will apply the forces on the three stringer here. So let's go back to the Excel file. So whatever the result here will be divided into 3. So yeah. And then damping 0.03. So FB, which is the frequency generated by doing the free vibration analysis earlier, which is 2.6195. 2.1695. For the gamma, uh, I'll be using zero point 0.8. For the N for walking, 8. N for jogging is 2. KFB for walking is 1. KFB for jogging is 1.08. And then FO for walking is 280 newtons. And then FO for jogging is 910 newtons. So what I did is I just put this formula, and then I have created my time history function for walking and for jogging. So what will I do is I will just copy this and then paste it on MIDASGen. So go to time history function and click the add time function to add the function, and then here we can paste our time function. So let's change this first to force, and let's name this as walking. Then paste. Then you have your time history function. Click apply. Next is for jogging. Then apply. Then for the crowded condition, we'll be using a sinusoidal function. So this is the spreadsheet for the crowd condition. So for this condition, in accordance to the Eurocode, this is the formula that we will be using for the force. But in MIDASGen, the inputs is as this: A plus C times T times E raised to negative D times T times sine 2 pi F times T plus PA times pi over 180, which is like this. So if you look at this and compare it to the formula that was used in Eurocode, you can say that it is almost identical. What you are going to do is you will need to get the value of the amplitude of this formula, which is this. So this is the formula of the amplitude A, this one, and then the remaining parameters like the C, T, E, and D, T will be set into 0 so that this will become similar to this function. So in this spreadsheet, I've already computed the A, which is into kilonewton. So this value, I forgot to tell, is on Pascal, or in a unit of pressure. Then you must convert it uh, into a force. So what I did here is I multiply this uh, pressure into the tributary width of a single stringer, and of course I divide the result of this also into 3. So I have here now my A, Actually, I can add this function to MIDASGen, but I just show you how we can use the sinusoidal function in MIDASGen. So I'll be using 0.125 for A and uh, an FB of 2.1695, which is F here. So let's use the force, and then A is 0.0125, and then the A is the F is 2.1695. Let's name this as crowd. Let's show the graph. So as you can see, it's almost the same from this time mystery function that was generated the um, in the spreadsheet. And then click OK. So let me check. Okay. Next, after we add our time mystery function, we can now add our forces. So to add our forces, we can use dynamic nodal load. So what we will do is we will apply the forces on the nodes acting on the stringers. So what we need to do is we will look for the step length of the uh, we need to look for the step length uh, of the load. So to get the step length of the load, what you need to do is you multiply your uh, natural period to the speed of uh, the force. If it is walking, uh, the natural period times 1.7, or uh, if it is jogging, natural period times 3. So natural period is just the reciprocal of the frequency. So there you go. Reciprocal of frequency times speed. And then for the arrival time for each step, so uh, it is just the step length times your speed. So as you notice also, I have here a, a table. So this table, I will be using this to add the nodal loads on the model. So I forgot to add. This is for the walking, for jogging, and then this one is for the crowd or crowded condition. So what is important here is the step length. So to generate the nodal loads, so in this model I have already generated the nodal loads. So let me just teach you how we can model those nodal loads. So to model that, or to add that loads, so these nodes, what we can do is we can translate the nodes like this one, this tree. So if we go to node and element tabs and then click under nodes, click translate, and then so it is on x direction. So you will just put, for example, your step length is 0.2, for example 0.2. So I'll just use 0.2 so that we can see the nodes here. So dx will be 0.2, dy is 0, and then dz is 0. So next, you will put the number of times. So in this part, this will be like the number of steps on the bridge. So if it is a 48-meter bridge, so it is a 48-meter bridge and then divided by 0.2. So you have a 241 steps. So let's try 241. And then what's important here is you must intersect the frame elements so that on each step, the nodes will be intersected to the element. Then click apply. So as you can see, there are nodes that was added to the model. So that's how you can add your step length if you haven't added first, or if you don't have yet your step length. So you may use the translate command. And then also the advantage here, so for example, if you want to generate first the step length here, you may change the start node number. Like for example, user let's say user defined, then set it to 1000, or let's say 10,000, so that when you look for the node number of that nodal elements or that nodes, to apply your forces, so you will only look for 1000 and above. And then for the second stringer, let's say you will put 2000, and then 20,000, then from 20,000 to 20,001, 2, 3, and so on will be for the will be the nodes for the second stringer, and so on. So let me show you what I'm saying. So I'll just display the node number. So in the stringer 1, I use 1001 for the first step, and then 1002 for the second step of walking. And then for jogging, I use 1101 and then 1102. So this is the first step of jogging. This is the second step. For walking, this is the first step, and then this is the second step, third step, and so on. So so by doing that, you can create a table like this, which you can just copy and paste it to uh, to the uh, to the table on MidasGen. So how we will add this nodal loads? So to add the nodal loads, first let's us select a node here. This will be like the initial node that we will be applying a force. So load, and then dynamic nodal loads. So let's say walking, and then direction is dz, the arrival time is 0, and then scale factor will be -1 for downward action. So to do that manually, so let's for example, I will select this 1001 node, node number 1001. The arrival time for this node will be 0.46. Apply, and then for the 1002, node number 1002 will be 0.92, and so on. So that's how you do it manually. So it will take a longer time if you do that. So what we will be doing is we will click it here beside the dynamic nodal loads, and then the table will be opened. And then after that, what I will be doing is I will delete these values first. So you have zero nodal loads applied to the model, and then I will just copy all of this. So this is for the walking. So in case that there is an error while pasting your tables here, it means that there are errors on the input values. Like for example, let me show you. Like for example, I mistakenly set this into 1, which is we don't have a load case 1. We only have walking, jogging, and uh, crowded condition. So let us try to paste this table with that error. So you can see at the message window, it will not accept. So meaning what will you paste here? You must double check it, and then but Midas uh, can check it for you if your input was correct or not. So let's copy again and then paste. Next, this one, and then the last one for the crowded condition. And then after that, so let us just discuss the arrival time on the table. So as you can see, the arrival time for this walking is 0.0461 for the 1001, and then for the arrival time of the 1002 is for 0.461 plus 0.461. So it is if you can imagine, it is like you are walking on the uh, on the on the pedestrian on a certain time until you reach the last until you reach your last step or the end of the pedestrian on a certain time, which is likely you will end up at the end of the 48-meter bridge 28 seconds. Same goes if you are jogging on the bridge. So logically speaking, uh, you need if you are jogging on the on the on the bridge, then your arrival time will be less. So in this table, the time it takes to jog on the bridge is only 15 seconds. For the crowded condition, as you can see, it is arrival time is 0, assuming that they are all in the uh, they are all in the bridge at the same time. So I think that's the application of the dynamic nodal loads. We can now proceed to the analysis. So let us go to results, and then but let me just double check. Okay, go to results, I mean analysis, and then click perform analysis. Take note that in this webinar we will be only doing the analysis, and then we will not be doing the design part here since we already discussed that from our previous webinars. So let's see. So let's go to results. To view the results of the time history results, go to results, and then under time history tab, you can get your results or your graph. Let us first discuss the results. Time history results, click this displacement, velocity, acceleration, and then so in this part you can see, or you can select where you want to uh, view your model, or at what time. So what is the displacement? If you want to view the animation, let's see. So let's see that only 0.5 seconds, and then let's only get the 10-second time. Start time 0.1, then okay, let's apply. So as you can see, again. Results. Walking. Okay, let's try 20 seconds and then apply. So you have your animation now. I think it is better to show the crowded condition. So there you go. So for the crowded condition, the 20 seconds, or let's see 10 seconds only. There. So that's how you can view the animation. So let us check the maximum acceleration. So first we will go to, we can check also the deformation. Let's try this deformation, and then crowded condition, max, DC, and then click apply. So the maximum displacement is at element 2030, which has a, so let's change it to mm, 0.59 millimeter displacement. Let's check the acceleration. So the acceleration on the element 2030 is 0.11 meter per second square. So to generate the graphs, So th graph and then th history graph. Click define function, and then select this displacement, velocity, acceleration, add new time function. Let's view the 2030 number 2030 acceleration. So name acceleration, z-axis, and then crowd. So components, dz, apply, or click OK, click back, and then add from list. Horizontal axis must be time. So the graph title will be acceleration, z-axis or z direction, and then crowd. So this is the um, time history graph of the crowd condition for the node number 2030. So it has an acceleration of negative, 0.11 at 39 seconds. So if you want to view the other cases, like for the walking, jogging, so it is just the same. But if you want to check the tabulated results, you can go to, you can, this one, displacement can be done as well. For change this to and then you can sort this out to check the displacement of the bridge. For the other results, you can check it here on other results that you want to display on your model. So I think that's the end of this presentation. If you have uh, more questions about the topic, you can put your questions on the question tab and we will answer it for you. So thank you, and uh, have a nice day. God bless everyone.
Hello, everyone. Thank you very much, Engineer Edric Tan. For now, we will be proceeding with the question and answer. So, Engineer Edric will be choosing some of the questions he would like to discuss through an open mic. But you can send your questions to our question 3 menu from our question 3 menu.
Okay, so there are some questions here from Engineer Muhammad. He said that on crowded condition, arrival time is zero. Why is that the crowded condition arrival time is zero? So for the crowded condition, it is zero because you assume that all the live loads acting on the bridge at the same time, but your loads will be sinusoidal, since sinusoidal is the load is the forces that we applied on that uh, on that condition. And then another one for from Engineer Roger. The pedestrian bridge constructed by MMDA, sometimes used by bicycle or even motorcycle, is this considered in the design load criteria? So my assumption here in my model is only uh, person are are uh, considered in the model. So that's why I don't consider the bicycle or even the motorcycle. But if you have your own condition, like for example, there will be a motorcycle that will pass on the bridge, then you can consider the load of the motorcycle and the bicycle on the bridge. And then there are also questions if we will be sharing the spreadsheet and the text document of the node and elements. We will share the spreadsheet and the text document of the node and elements um, after this webinar. We will email it. Another question from Engineer Mark Alexis. Sir, how about the release in trust? For the release in trust, you can go to uh, but if you uh, but if you have already assigned your member into a trust element, you don't need to release the trust. But if it is a um, general beam or beam element, if you want to release that element, you can go to boundary tab and then click beam end release. So if you use truss element already, you don't need to release the truss. So I think that's all of the questions. If you have more questions, you can email us at pageinquiry@midasit.com. So thank you everyone.
Thank you once again. Thank you, Engineer Edric Tan, for doing the presentation for today. Um, so this is actually the end of the series, the training series for RC application. For those who have additional questions, you can email our technical engineers at phinquiry@midasit.com. And then we will also be you can now download the handout through the three menu. We have uploaded the vibration analysis for steel, pedestrian bridge handout, and in the three menu for handouts. And if your certificates will be sent through email. We just have to finalize the list of engineers who have completed the training series, and also we will be sending you an email regarding your workshop assignment. Tomorrow we will be doing another rerun of this today's webinar. So if you have colleagues, friends, or structural engineers who have missed this webinar, they can still attend for tomorrow's training or rerun. And then we will also be we have also already started planning for the next training series of training for Midas Gen. Most probably it will be first steel, and hopefully you can still attend our training session, our series of training session for the coming months. Once again, this is Michael John Tungkol. Have a nice day ahead and keep safe. Thank you.